All right, so yeah, yesterday we talked about these terms, and we talked mainly about two very important terms, the system and the surroundings, all right? And that's what we really need to kind of get encapsulated in our mind. What do we really mean when we're talking about the system, and what do we really mean when we're talking about the surroundings, all right? We also need to keep in mind our terms that were associated with energy, right? So we've got kinetic energy and potential energy. I think that's pretty straightforward, energy of motion versus energy that's stored in some way. And then we've got heat, which is this transfer of thermal energy, okay? And so all these terms become very important. And what I want to do is draw a little diagram to kind of solidify these terms in a little more of a graphic fashion. So if you've got the title calorimetry down, that's great. I'm going to switch to the Smart Notebook, and I'm going to then draw a little picture that I use to represent this stuff. Now, yesterday, we talked about a chemical reaction where I drew a little beaker, and that beaker had some water in it and some hydrochloric acid and some magnesium, and I hopefully got across to you. Well, I'll ask you this question. In my little, well, let me draw it up just to kind of, again, get your mind going straight here. So if I've got a beaker here, and let's say that we've got a lid on it, and let's say that it's made out of lots of styrofoam so that it is what is called isolated, which means no energy is going to be able to leave and come in, and no matter is going to be able to leave and come in. So I've got here some HCl, and I've got here some Mg. It's going to produce some H2, which is going to bubble away, produce some pressure in here, which is just fine, and it's going to make some MgCl2. And of course, that's all dissolved in some water. All right, well, you tell me, what is the system here? What are we studying? What are the things that we want to learn about? What's the system in this picture? Yep. The HCl and the Mg, it's also the MgCl2 and the H2. It's the reactants and the products of the chemical reaction we're studying. So all of our reactants and products here, I'll draw a couple of lines that come from them. All this stuff is what we call the system, all right? Now, it's not what we mean by an isolated system, right? That term isolated describes the container we're using. And I know it uses the word system. That's unfortunate, but it's not the system we're studying. The reactants and products are the system we're studying. Excellent. What's the surroundings in this case? Yep. The water. And the surroundings essentially is the substance or substances, it could be more than one, that are essentially nearby this chemical system that allows it to catch the heat if it's produced, or give heat in if the chemical system needs energy, if it's endothermic. So the water itself is the surrounding. Excellent, all right? And then we've got what I would call the surrounding surroundings. The surrounding surroundings would be the rest of the furniture that's in the laboratory, and the people and the air, and our styrofoam cup, our isolated system, hopefully keeps the surroundings away from our chemical system so we can study it, all right? So that's the whole purpose of doing it. Now, what are we doing, and why are we doing this type of thing? Why do we need to separate it out? Well, it has everything to do with studying energy transfer. So now, instead of me drawing a picture of a beaker or a styrofoam cup, I want to draw the system and the surroundings as if they're just a container for energy. I don't want to really worry about the actual styrofoam cup and the actual chemicals. I want us to kind of think of it just as an energy reservoir, something where energy is going to be put. So I'm going to clear this screen. Let's just get a new slide here. And so instead of drawing beakers and containers, I'm going to just draw a rectangle, very simple rectangle, right? And I'm going to let that rectangle represent my system. That's the chemical system. And you can think of this rectangle as a bank, all right? Like a building that holds something. Something that's just holding, in a bank it would be money. In this case, it's energy. So let me just make a simple little bar graph to represent the energy that is in that system, all right? And again, this system could be the magnesium and the hydrochloric acid producing the, magnesium chloride and the hydrogen. But I'm just drawing it graphically as something that has a bunch of energy in it, all right? There's energy within that stuff. In actual fact, there's two forms of energy. We'll learn about that today. The two forms of energy, so I'll break this in half. The two forms of energy are EK. There's kinetic energy because the particles are moving, they're wiggling. And there's EP because there's energy stored in the bonds. So now I want you to think of our chemical system not as being physical chemicals, but as being something that holds energy, okay? Like your bank. Your bank holds your money. You may have 2 or more bank accounts. Your total amount of money would be the sum of all of your bank accounts, but you may have a checking account and you may have a savings account. The energy within a chemical system, there's a total amount of energy, and in that system, some of the energy is in the form of kinetic energy. The particles are wiggling, or they're vibrating, or they're moving, and some of it is in the form of potential energy stored in the chemical bonds. Okay? So that's our system. That's what we want to study. That's the thing we can't see. We cannot simply look at some reactants in a cup and say, oh, look, I can see it wiggling. There's some kinetic energy. Let me write that down. That's good. And, oh, look at there. I can see the bonds. I know how strong that bond is. Let's write that down. I can't just, it's like I don't know what's in the bank. It's like having a bank account and having no knowledge about how much energy is in there. Gee, I wonder how much money I have. I have no idea. I can't tell. All right? That's the trick of thermal chemistry, to be able to do some experiments and figure out how much energy is in that thing. How do we do that? We do that by looking at what happens to the surroundings, the water in this case. I'm going to let the surroundings just be another rectangle, except this one's going to be really long, and actually it's so long. Actually, no, I'm not going to make it infinitely long. Let's just put a box there. All right. This is going to be my surroundings. Surroundings. And that's essentially the water in this case. In most cases in this course, the water is the surroundings. And that water also has some energy, all right? And I'm going to make a pile of energy in there as well. And I'm going to make it a bigger rectangle because the water is a lot bigger than the chemical elements themselves. There's a lot more water around, so there's a lot more. And again, it also has lots of energy, and we're going to put here EK. We're not worried about the potential energy in the water because we're not going to be chemically changing the water. All the water is going to be doing is catching the energy that comes from the system. When the chemical reaction happens, it's going to spit some energy out, it's going to give it to the water, and the water's going to warm up. The water's not going to boil, hopefully, or we'll have to change our experiment. The water's not going to decompose. So we're not chemically affecting the water, we're just affecting its temperature. So it's only the EK we're affecting. So what are we doing? Well, here's essentially what a calorimetry situation does. We take our coffee cup calorimeter with a nice fitting lid, and this is actually crappy because I can't find my good ones, but you get the idea. That look at how isolated that is. There's no way energy can get out of that. Yeah, thank you for giggling, because look at the holes in it. It's all over the place. This is terrible. But this is not too bad right here. So we put in our water and our reactants. We put in the other reactant. The reaction starts. We put a thermometer in. We measure the temperature before. Then we measure the temperature afterwards. And that change in temperature of the water tells us something. And that's what calorimetry is. We put the reactants in. The energy of this system changes, and some of the energy gets transferred to the surroundings. Some of that thermal energy goes to the surroundings. When thermal energy moves, the transfer of thermal energy from one place to another or from one thing to another, we had a definition that defined one of our important terms yesterday. Does anybody remember what that word was? If the thermal energy moves from one place to the next, what do we call that? Yeah, it's called heat. Do you remember the symbol we had for heat? It was a Q. Q. All right? This, right now, is what we want to learn about today. We want to learn that if the surroundings heat up, how much Q did it get added? how much heat did it get, all right? Because eventually, we're going to get to the point where the amount of Q that goes into here is the same amount of energy that came out of the bank, right? Because we have a conservation of energy. If the system loses some energy to the surroundings, then the energy that the surroundings gains must be exactly equal to the energy that the system lost. So by measuring the surroundings, by measuring how the water's temperature changes, we can get an idea on what's happening in the system. Because we can't actually see the system, but we can measure the surroundings. We can measure it by temperature changes. And that's what this is all about. So for today, we're going to learn about the Q. How do we calculate how the surroundings changes, and how do we determine the energy involved? In the next lesson, we'll learn about how that relates to the system, so that we can then make the step of, if some energy leaves, how much energy did the system change by? So today we're learning about the surroundings. We're learning about what happens when a surrounding material gains in temperature, gains in heat, or loses, temperature decreases and loses in heat. All right? That's my introduction essentially. So calorimetry, and I've got a little bit of a description on what calorimetry is, and you can write that little definition down. I found my far superior coffee cup calorimeters. Not only does the lid fit far more snugly, it's 2 cups put together. Wow, that's twice the insulation. It's practically perfectly isolated. Not even close. But it'll do for us. Our expensive scientific equipment here at LCCBI. But it'll do for what we're doing. It'll do for an introduction. Again, the calorimeter. We call it a calorimeter. What a great fancy term for 2 coffee cups stacked together with a coffee cup lid. It's not bad. The idea is that it's isolated, that it's keeping the heat energy in so that it can't get into the surroundings, because we only want it to get into the water, the surroundings. This will do for what we're doing. Here's some other types of calorimeters that you can get if you're doing, far more precise work than what we're doing. This here is the same piece of apparatus. This is called a bomb calorimeter. What a great term. Essentially, a bomb calorimeter is, it's got to be fortified because there's combustion reactions that go on inside of it. You take the top off, you've got an internal reaction chamber. There it is there with the top of the reaction chamber off of it. You put some fuel in there, whether you want to check for the energy that's given off when some gasoline is burnt, or even some propane. You'd put some gas in there, you'd put the thing on. The top has an igniting system so that when you want to measure it and you get everything closed up inside there, and there's usually ice or water that goes between one metal container and an outer metal container, and then you ignite it with a spark, it burns and makes a bang, right? That heat then goes into the surroundings, the metal and the ice, if the ice melts or the water, and through the calculations I'm going to teach you, you can figure out exactly how much energy came off of that particular thing, all right? So that's if you were to do combustion reactions. Obviously, I can't do a combustion reaction in my coffee cup calorimeter because that'll just end with a big pile of styrofoam that's all melted or burnt up. I can't do that in this, all right? You can even test calorie content, and that's where the term calorie comes from. It's an energy term. So a calorimeter is a calorie measurer. We measure it in joules instead of calories. But you could measure calorie content in food, because when we ingest food and we digest it and it goes through the system and cellular respiration and blah, 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 biology, blah, 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 you know what I mean? We're essentially burning that food in the, cellular mechanisms of our body. They can get the same calorie content by putting it in a bomb calorimeter, burning it up, burn the food, literally start it on fire, burn it, catch all the heat, and that's the energy content that's within the food. So you can measure calorie values within food by burning it up in a bomb calorimeter. All right? That's essentially calorimetry. So we insulate, and this is really, we're messing up the terms again. We insulate a system from the surroundings. But when we say we're insulating the system from the surroundings, what do I really mean by this term surroundings down here? Yeah? The surroundings. So confusing. We want to keep the water and the thing that is going to catch the heat, which we call the surroundings, isolated from the outside world. We don't want that heat to get into the outside world. So that last statement, we really mean the surroundings. We've got to keep it isolated. All right. We'll get it. We'll get through it. Okay. Now, some of these next slides, and I don't want you to write this all down. I do want you to write the amount of energy. Write the first bullet. Write the first bullet. And then we're going to just read the next ones. And I'm going to then put the equation up. And I'm going to just then define them in a much quicker way. I find this is overkill. The amount of energy that can be transferred into or out of a substance to facilitate a temperature change depends on 3 factors, and then don't write any more until I tell you to start writing again. So don't write down number 1, mass. I'm going to put that in an equation, and I'm going to express all of this information in a far quicker, more efficient fashion. But 1 is obviously mass, all right? If I have a tiny little amount of water, and I put that little amount of water out into the sun, it's going to heat up quite quickly because there's not a lot of water to heat up. That energy is going to cause those vibrations to happen very quickly, and it heats up very quickly. If I have a large swimming pool of water and it's out in the sun, it's going to take a lot more energy to get it to heat up to the same temperature because there's a lot more molecules to put the energy into. So the more matter you have, the more energy it can take in to heat up or give off to cool down, right? So mass is 1. The more mass you have, the more energy that it will take to heat it up. Again, don't write it down. We're just going to write it down in a moment. The second thing is something called the heat capacity, and that's a fundamental property of the matter itself. Water is very good at absorbing heat energy, right? The reason water is very good at absorbing heat energy is because it's got lots of bonds. Not lots, but it's got 2. And it can vibrate, rotate, and translate. Yeah, that's right. Don't make me do it. I'm not going to do the vibrate, rotate, translate dance. It is fun, though, I must admit. It's one of the funner things I do. But I'm not going to do it. It can move all in these different ways. You can visualize me doing it. Anyway, if I have something like here, I've got some bronze. Bronze isn't a very good one. I got copper. If I've got, I think it's copper. I got copper. That's copper, definitely. If I've got something like copper, copper is made up of just a bunch of copper atoms that are in a lattice structure. It's not able to move and rotate and translate. It doesn't have bonds that it can wiggle back and forth. The only thing the copper atoms can really do is shake back and forth, which means if I add some energy to it, it's going to shake back and forth quite quickly because all of the energy can go just into vibration. It heats up quick. Metals and copper, stuff like that, heat up quick because there's nowhere to store the energy. Something like water, you can store all kinds of energy in a water molecule. You can make it rotate, you can make it vibrate many different ways. It's able to suck that energy up. You can see here we've got some heat capacities. For water, it's 4.18 joules per gram degree Celsius. It will absorb 4.18 joules for each gram that it has and each degree Celsius that it moves up by 1. If I look at some metals, and I don't have copper, but iron is here, 0.44 joules. For each gram of iron and each degree Celsius it goes up, it can only absorb 0.44 joules, but water can absorb 4 joules. Water is 10 times better at storing and absorbing energy than iron is, or any metal. Aluminum can absorb a little more, but it's not great. Ice, not quite as good as storing energy as water, because again, it's locked into its crystal structure. It can't rotate and translate as easily. Methanol, that's a type of alcohol. It's still not as good as water. Water is a great heat absorber. Okay? So the specific heat capacity is given the letter C. It's a fundamental property of all materials, and it kind of describes how good it is at absorbing energy. And the last thing is the temperature change. If you have something absorb energy and it only changes by 2 degrees, then it's absorbed a little bit of energy, but if it changes by 4 degrees, it's absorbed twice as much energy. So the greater the temperature change, the greater the energy that's been absorbed. And we represent that by delta T, and I think we're all aware that a delta means final minus initial. We'll do some calculations on that. So what do I want you to write down? Let's go back to this, because I don't like the fact that it's so much to write down. All right, so all I want you to write here is Q equals MC delta T. And I'm going to do this the good old-fashioned way like I used to do when I teach physics. I'm now going to just define these things with a nice arrow right there. That Q is the heat. That's the thermal energy transferred. That's how much energy either came in or went out, depending on the sign. And the units are joules. M is the mass of the substance. Its units, grams. If we were doing this in physics, which you may have done, you would have used kilograms maybe, and then a different C would have been moved over by 3 decimals. Chemists like grams. I don't know why. We don't like those great big masses. Kilograms, they're scary. So big. Drop it on your toe, it would hurt. C, the specific heat capacity. The word specific implies that it's for 1 gram of substance, all right? And I'm going to just put the units here, and that unit is joules per gram degree Celsius, with both the gram and degree Celsius on the bottom. You may come across questions, I hope I don't have any questions in my handouts, but in the future you will come across questions that just deal with the heat capacity, all right? Now don't write this down, but the heat capacity, which is a little different than the specific heat capacity, is if you combine the M and the C. If you combine the M and the C, chemists call that capital C, and they just call that the heat capacity. Don't write that down. But that's why I put it in yellow. I don't want you to actually write it. Don't worry about it. But sometimes scientists will just talk about the heat capacity of a substance. And what that simply means is, well, let's take the number of grams, right, the total mass, multiply it by that specific heat capacity, which is like kind of how much each gram can do, and then that's the overall heat capacity, all right? So that's a term you may encounter in the future. We're going to just deal with the specific heat capacity, and then I'll give you the mass, and you can then, what you're doing is you're figuring out the heat, the overall heat capacity. But that's the little things that you'll learn about in the future. Okay, so don't write that down. That's not important. It's just a term you may encounter. And here we've got the temperature change. All right. I've got a question in my worksheet that has Kelvin in it. Even though this says joules per gram per degree Celsius, a degree Celsius degree is exactly the same size as a Kelvin degree. So you don't have to convert Kelvin. You can just subtract Kelvin temperatures as well, and you'd still be able to get the same answer because it's just the difference. So if you get numbers in Kelvin, you can leave them in Kelvin. You can just subtract them. You'll still get the same answers. Temperature change, delta T. I'm a fan of T2 minus T1 instead of final minus initial. That's just my physics background. If you like final minus initial, that's fine with me. And it can be in degrees Celsius or Kelvin will work. So what we've done at this point is we've learned how to calculate how much energy the surroundings are gaining or losing. And that's good, because the next step will be to apply that back to the system. So we're now just looking at the surroundings that are in my coffee cup calorimeter here, the water here. We're just looking at that. We're just starting so that we can apply it next to the system. Let's do some example problems. Okay. Okay, there's the equation. No need to write that. We just did that thing. All right, there we've got some practice problems. And again, we're just copy and do them, you know, good old examples. Right now I'm handing out a worksheet. It's got 14 questions on it. It's not all calorimetry. It's also going to contain some questions that you're going to be doing next week while I'm away. So there'll be a video, right? I'll do examples. So this sheet will also be used for next week's, I think it's Tuesday's lesson, all right? So keep that in mind when I say the calorimetry worksheet and I give you numbers off of it. This is the guy. If you see where this is heading, by all means, go ahead. All right? We've got two temperatures there. You can get a delta T. We've got a mass there. That's obvious. In this question, I'm not giving you the heat capacity because I've put a table right there beside it, so we can get the heat capacity off, or the specific heat capacity off of the table. In many of the questions on the sheet, if you need the specific heat capacity, I give it to you. In textbook questions, they tend to have a table nearby, very much like this, that they make you go and look up the heat capacity if you need it. So, determine the amount of energy. I'm looking for, well, determine the amount of energy required. In other words, that's a transfer of energy. That's a transfer of thermal energy. So what am I determining? Which of my variables am I solving for here? Yep, Q. So I'm looking for Q. Q, I want to do it in yellow. Q equals MC delta T. And you know what? Again, writing down data is great, but we're grade 12 veterans. If we can just pluck the data out and put it in, that's great too. I'm all for plucking data out and putting it in. Mass, 25.0. Again, you know my views on units. Some professors will be picky about it. I'm not picky about it. I'm going to include it on this first one just so I can show you the way the unit analysis works. The C, what is it for? What are we dealing with? Water. What's my C? Yep, 4.18, 4.18, and that is joules per gram degrees Celsius. And by the way, that C is the only one I'm going to make you memorize, because we're going to be dealing with water over and over and over again. That's what's going to be our surroundings, which means if I tell you a question that you've got a coffee cup calorimeter and it's got some water in it, I'm not going to tell you the C of water. We're going to use that one so many times that I'm going to expect you to memorize. Delta T, and we can do this all in one shot. We've got to be very careful which is the second and which is the first. Starts at 25, goes to 75, so 75 minus 25. That's very important because if you switch it around, you get a different sign. And that sign is going to tell you whether the heat content went up or the heat content went down. And that's going to be very important in the near future. So, this has units degrees Celsius. The reason I put the units, this guy will cancel this guy. The grams will cancel the grams. And notice we are left with the unit joules. And I will take somebody's answer, and it's looking like 2 significant digits for the temperatures. That's what it's looking like. What do we got? Yep, right? 5,200 joules. Rounded to 2 significant digits. We like that? Supporters on that? I guess maybe to take the ambiguity away, 5.2 times 10 to the 3 joules, right? That would be scientific notation. Or we could even do it better, times 10 to the 3. I don't have it on my wall anymore because I took them down. It's on your sheet. What prefix is 10 to the 3? Yep, kilo. So we could say 5.2 kilojoules. That's also going to be something we're going to be doing a lot in this course, bouncing back and forth from joules to kilojoules. So that's a step that we want to practice. Okay, positive means that the energy content of the water increased by that much. In other words, if we were to say the surroundings was a bank account, the water's bank account has gone up a little bit. It gained a little bit of heat energy. Okay? All right, let's do another one. Now in this case, we're not dealing with water, we're dealing with iron. And I think this is iron. Now we're not going to do any questions where iron is part of the calorimeter. But if you were doing a problem on a true bomb calorimeter, and these are the types of problems you do in university, then you've got to take and figure out 2 MC delta T's. One for the water that's in the calorimeter, and one for the iron that the calorimeter is made up of, to get the total energy that was given off by that whatever, burning whatever you're testing, all right? So I don't have any true, questions where we're talking about a coffee cup calorimeter. It's not like I've got it encased in iron or anything like that, but you could encounter a question like that. So this time now the iron is absorbing some energy here. They tell us the energy to increase the temperature, and we're looking for the mass, all right? So again, our equation, Q equals MC delta T, and this time I'm looking for the mass. I like rearranging first, but I know some people like to rearrange after, so we'll do the after. We've got to be very careful here, because what unit is my Q in this equation? It's in joules. Notice the energy unit they've given us, kilojoules. What's the easiest thing? How's the easiest way to convert that thing? Yeah, Jess? Yeah, times 10 to the 3. Just to stick a times 10 to the 3 on the back end. Joules. So the equation uses joules. If you're dealing with kilojoules, you gotta convert it over. We're looking for an M. C for iron, 0.444. Delta T. Again, I like putting it all in one shot. Again, we've got to be very careful. From 45.5 up to. So 85 is the second one. 85.7 minus 45.5. Remember, we got to do these brackets first, and then we'll divide off. And I don't want to mess up the slide here, but I could divide by that subtraction. I don't have that. What is that? 40.2? Looks like 40.2. Anyway, got to divide off 40.2, got to divide off the 0.44. M equals. Do we have a number? Jess, what do you got? 68.4, looks like 3 significant digits all the way along, grams. We like it? We like it? We don't like it? We do like it? 67.5. Didn't get the 67.5. No, it's looking like there's a lot of support for 68.4. Anyway, do we need multiple? Do we have a check on it? We like it? I don't know what's going on. All right. Questions, concerns? Okay. Other than Elena? I'm sure Elena has concerns. Why is my calculator not doing it? Did you forget it fixed? Sure, a little entry error. I'm sure in the grade 11 physics, you may have even did a little experiment. Does he have you do experiments where you heat up the piece of metal and put it in water? Does he have you do that? Huh. I should lend him my coffee cup calorimeters. It could easily be done as an experiment. We could take a piece of aluminum, because we've all got all kinds of these pieces, get some water boiling, get it into that boiling water, let it sit there for a long time. We would know the temperature was 100 degrees. And then plop it in some water that we know the temperature, and we could actually measure the heat capacity of this, doing a very simple experiment like that. 100 degrees, get it in the calorimeter, let that temperature adjust, and we could do that. And you know what? I would love to do that. It would be a great little exercise. But again, with me going away next week, I'm going to run out of time. But that could easily be done. Now, that's not really chemistry. If we were to do an experiment, heat up the aluminum, put it in the water, figure out the temperature change, solve for the heat capacity, right? We would just be doing a physical property of this aluminum. That's physics, really. How much heat can it hold? So maybe that's something I could suggest to Mr. Petrus to do. We want to learn how to use this so we can get into chemistry. Let's look at some chemical reactions and see how they do. Okay. What are we looking for in this one? What are we trying to find? Yep. T2. Now, you know what? You could substitute it all in and have T2 in there, but that becomes a little tricky. You can easily do it, right? The mathematics isn't bad. But if you're not great at algebra, what I suggest you do, if you're looking for a T2, like in this case, I would solve for delta T. Solve for delta T. As soon as you know what the temperature change is, you can apply it to what that first temperature was and tell me what the final temperature is. So that's kind of a little bit of a trick. You could put in T2 minus 22 and rearrange and solve, but you could find the delta T and apply it to that. That works as well. Q equals MC delta T. And we've got 1.25 times 10 to the 3 joules. The mass is 50 grams. We've got aluminum, so we can check our table, 0.900. And delta T, and if we then divide off both of those, what do we get there for a delta T? Oh, hold on 1 second. We need to check a sign here, all right? What would the final temperature be if the 50-gram piece of aluminum had 1.25 times 10 to the 3 joules of heat transferred into? If the energy is going into it, what's the sign on this energy? What's the sign on the aluminum's energy bank account if energy is going into the aluminum? Yep. Negative. If you put money into your bank account, positive. Positive. Because energy is going into the aluminum, this is a positive energy transfer. We're putting energy into the aluminum. That means this is positive, and therefore my delta T will be positive, which makes sense. If you're going to put energy into the substance, its temperature is going to go up, a positive temperature change. That implies energy has been added. So what do I get here for an answer? What do we got? Been babbling away here. Shauna, what do you got there? You were pushing the buttons on a calculator. It looked like you were doing something. Were you spelling little funny words, turning the calculator upside down? Yeah, that kills some time. Don't make me go to Jessica. Don't make me do it. What do you got, Ryan? 28. And actually, we got 3 significant digits going. 28.0? 27.8. We better keep our 3 significant digits. Let me get the eraser here. 27.8 degrees Celsius. Now that's the temperature change. So you could rearrange the equation, but if you think about it, if you start at 22 and the temperature change is plus 27, you're going to add those 2 things together. 22, it's 0.0 degrees Celsius. Look at that. That degree's in the wrong spot. Degrees Celsius. You get the idea. Plus 27 point, oh my God, that's an 8. Look at that. Is that supposed to be an 8? That's horrendous. What do I have here? 49.8? 49.8 degrees Celsius. Okay? All right? All right. And there are some questions that you can do right there. Oh, wait a minute. And I left off, oh, that's funny. I had added one more question to this. You know what? You can write that down. That's okay. And I changed this PowerPoint online. This is actually an old PowerPoint. You can also actually do on the calorimetry worksheet. So I'm assigning this as well, even though it's not written down. You can do 1, you can do 2, you can do 3. Yeah, you can do 4, you can do 5. You can do 6. Yeah, 1 to 6. Now, I do have one more example I really want to do. Let me see if I can find it for a second. I do have one more example. Write that down, right? Did you get that down? And then 1 to 6. 1 to 6. And now I have got to go. Let me just see if I can find it. Oh, goodness gracious. Goodness gracious. I do have one more. Calorimetry. We did that one. There it is. There's my number 4 right there. There's my number 4. And I need to go over that one because you need this in order to do like number 4 on this page. Same with number 5 and same with like number 6. once we have this written down, I'll go to the Smart Notebook program and we'll do it on a white page like that. So this is a little different. Here we've got two samples of water. They're at two different temperatures, and we're mixing them together. So the hot one is going to give a little bit of its energy to the cold one, and the cold one's going to warm up a little bit, and they're going to get to some temperature that's the same in the middle. This is like putting two of our Q equals MC delta T equations together as one. You would have done this with Mr. Petros. I actually talked to Mr. Petros on how he did these types of problems. And it's going to be the same way that I do them. So has everybody got the question written down? Okay, so let me just get a blank page here. So, and I wish I could get a darker pen. I think red is probably better. It won't let me actually pick a black, will it? Oh, it does. Beautiful. So, what do we have? We have a sample of water and a second sample of water, and I'm actually going to ask you for the data on this. If we call this sample 1, all right, actually, we use 1 and 2 for before and after, don't we? So I can't call it 1 and 2. So let's call this sample hot. We'll call this H. And what is the mass of the hot sample? What is the mass of the hot one? Sorry? 35 grams? 35.0 grams. And the C of the hot sample is what? 4.18. Excellent. Sorry? What? Did you say 4.18? No, you didn't, obviously. Well, we're dealing with water, right? So it's 4.18. We got two samples of water here, don't we? Two samples of water? Okay. And a T2, all right, and a T1, and we know what the T1 is. What's the initial temperature of that water? The hot one. Yep. 325 Kelvin. And T2, well, that's what we want to find, right? We want to find that final temperature. We'll call this cold. What's the mass of the cold? I don't recall because it's not on the screen anymore. Sorry, 45 grams? 45.0 grams. The C of the cold is, it's water, isn't it? Now, in the questions on the page, it not necessarily it's water mixed with water, but it might be like a piece of iron put in water. So you might have two different C's. In this case, the C is the same because they're both water. 4.18. T2, unknown. T1. What's the T1 of the, sorry, 278? 278. Excellent. Kelvin. Now I do have to put a couple more marks here because I want to make sure I differentiate between my 1s and 2s. So this is like T2 hot and T1 hot and T2 cold and T1 cold. Okay? Well, essentially, the Q, right, of the hot, the amount of heat that is given up by the hot is going to be equal to the Q of the cold, the amount of heat that's given up, that is accepted by the cold. That's the law of conservation of energy, right there. It states that the Q, the heat that is lost by the hot one, is going to be gained by the cold one. Does that make sense? That means that the exact amount of heat that's lost is gained. Except there is one difference. If the hot one is losing energy and the cold one is gaining energy, I do have to add one more thing here. Yep. Yeah, the hot is going to be a negative sign because it's going to be losing energy. Make sense? So now we're ready to input our information. I'm going to extend the page here so that we can get a little further down. So negative, M, hot, C, hot, delta T hot, but I'm going to put here our T2. What's going to be true about both T2s? after we've done mixing them, and the hot one is cooled down, and the cool one is warmed up, what's going to be true about both of the T2s? Yep, they're going to be the same temperature. So I don't really need to say T2 hot and T2 cold because the T2s are equal. Let me just put that off to the side here as a statement. T2 hot equals T2 cold, and let's just call that T2. The same thing in our equations. So T2 minus, and then it's going to be T1 hot, that's different, and then it's going to be sorry, do you see what I've done here? I've put a cold, and those are supposed to all be hots. I apologize. Mass cold, C cold, T2 minus T1 cold. I haven't put these in past years. I've reintroduced it, so I haven't done these in a while, so I'm tripping over it as well myself. You grade 11 veteran physicists should be helping me here. Let's put our information in. Minus, and what was that mass? I can't move my screen up, can I? 35? 35.0. 4.18 T2 minus and 325 mass cold, what was it, 45 4.18 T2 minus minus, what is that temperature? 278. Now we got to rearrange and isolate for T2, and we've got it. We've got to do some algebra here. What's the best way to do this type of thing? We want to multiply it all the way through and then isolate for T2s, or do we want to put some numbers together? There's many ways to solve for this at this point in time. And I'm trying to think of the most efficient, because we could do this times this and then FOIL that through and then isolate. Or I could isolate these guys. I think you just have to FOIL it through. I don't think there's much you can do about it. We can do one thing to simplify this, though. What can I do to simplify this before I get rolling any further mathematically? Elena? Yep, you can multiply that, but take a look also. We can do something to even simplify it even further. Yeah, Jenna? You want to bring the negative in? We can do that as well, but that's not that. But we have to do all those things. They're all good, but we can actually make this a little easier. Yep. We can cancel out the heat capacities because they're the same. Now, there's a question in here that has two different materials, water and a hunk of metal, and then you can't cancel them out. But we can cancel out this 4.18 right here. So yeah, let's FOIL it through. This 45 is going to go there, which means I'm going to have 45.0 T2, and I need that number 278 multiplied by 45. If someone could give that to me, that'd be great. Someone going to share that with me? 45 times 278? No? All right. Yeah, what do you got? And on this side, you could bring the negative in. Sure you could. So it would be negative 35 T2, negative 35 T2. And then negative times negative would make it plus. So what's that 35 times 325? Yep. So let's gather up our T2s. I would bring the negative over here to make it positive, so we're dealing with positives, and I'd bring this guy over to the other side. So I'd have my 11,375, and that's going to be plus 12, 4510 equal to 45.0 T2 plus 35.0 T2. So I can put those two together, 35 plus 45, that's 70, that's 80. 80 T2. And how about this big number here? Somebody got that put together? Yep.
23,800.
And now we're dividing off 80. Divide off 80. Divide off 80. And T2 equals. Now this will be in Kelvin because we've been working in Kelvin. What do you got? 298.6 Kelvin. And we've been dealing with 3 significant digits, so we need to round that. 299 Kelvin equals T2. And obviously it is at some intermediate temperature, and it's actually probably going to be a little closer to the cool one because I believe we had more cool. We had a little more cool than warm. All right, so that's the most complicated version of it. All right, but that also uses that conservation of energy that when one loses, the other one gains. Okay? All right, so that's the end of today's lesson. Yep. You don't have to, but if you'd like to, you can. It might make the math easier. Because it's a change in temperature, and because 1 Kelvin degree is the same size as 1 degree Celsius, you end up getting the same answer whether I converted them at the beginning or whether I converted it at the end. If we had converted it, our numbers wouldn't be so big on the left-hand side. Might be easier to deal with mathematically. You can convert if you like. In these questions, it doesn't matter which unit you use. All right? Okay, so that's the introduction to calorimetry. We learned how to deal with the surroundings, and now on Monday we'll talk about the system. Okay? And then on Tuesday, when I'm not here, we'll be putting together, and I've got it on the video, the system and the surroundings so that we can do a calculation on the surroundings and learn about the system. Yeah, okay. That is a good place to end.